Hello guys, welcome to eGate. Let us start power electronics. Okay, I hope you have covered maximum schedule of other subjects. So today we'll start with power electronics. Okay, now see, to cover power electronics you must have some basic idea of signal system. Okay, and some basic ideas of machine that will be used in drives and all. Okay, now drive part is excluded from our syllabus. Okay, but although then also idea of machine is needed. Okay, so let me talk about the syllabus that will be covering. Okay, so the syllabus that will be covering is, our content will be power semiconductor devices, in which I'll be telling you what are the switches that are required and classification of different type of switches. Okay, and the characteristic of switch. Okay, the ideal and practical switches. Then we'll cover single phase, then we'll cover the rectifier part. Okay, in the rectifier part, what I'll be doing is, I'll be covering single phase rectifier, okay, then single phase half wave rectifier, single phase full wave rectifier, and also single phase full wave bridge rectifier, full wave midpoint rectifier. Will also be covering semi-converter. Okay, full wave single phase half controlled, okay, half controlled rectifier, that is also called semi-converter. Okay, then we'll discuss about three-phase rectifier and different terms and different waveforms and different loads that are related to it. Okay, then I'll be covering choppers. Okay, in the chopper part I'll be discussing about, here also we'll have three-phase half wave and three-phase full wave. If time permits, we'll also go through three-phase semi-converter, but that is rarely asked. Okay, choppers. From chopper we'll have buck chopper, that is also called step down chopper, boost chopper, that is also called step up chopper, and buck boost chopper. Then I'll also classify chopper as class A, B, C, D, okay. Then in the chopper part, not only we'll discuss about continuous, for all these three we'll discuss load having continuous conduction, boundary between continuous and discontinuous, conduction, and discontinuous conduction. Okay, See, before 2018 or 17, mostly this was preferred or this was preferred. Okay, we were not discussing discontinuous conduction because it will take extra lecture. Okay, we are not discussing, but since now the question has, they have started asking from discontinuous conduction also, so we'll cover this part also. Okay, we'll be covering the discontinuous conduction part also. Similarly, in this all three, I'll be having the load as R load, L load, RL load, RL load with freewheeling diode, then RLE load, then RE load. Now in the RL load and RLE load, again I'll be having two cases. First is continuous conduction, and the other will be discontinuous conduction. Okay, even in the L load we can talk about this. Wherever L will be there, we can talk about continuous and discontinuous conduction. Okay, and in the power semiconductor devices, I told you that I'll be covering the characteristic of switch, then classification of switch. Different type of switches are there. Okay, unipolar switch, bipolar switch, unidirectional switch, bidirectional switch. Okay, semi-controlled switch, uncontrolled switch, fully controlled switch. So all that will be covering in that part. Okay, now see, in the rectifier part, diode circuit is also there. So as basics of the diode circuit will be covering here only. Diode circuits. Okay, basic of the diode circuit, like I'll be using diode and I'll be using different load and I'll be telling you. Okay, although it belongs to the rectifier part, okay, we'll be covering here only because it will have basics of this. Okay, then I'll have more things are there. So here I'm writing, I'll be covering SCR. Then in that characteristic of SCR, okay, VI characteristics of SCR, then about latching and holding current, okay, then on-state, okay, SCR, under SCR only this part will come first, second, then I'll be having on-state method of SCR, okay, then I'll be having in that various method will be there that we'll discuss. Then series and PR. Okay, you can also write here diode as switch. Diode as switch. Then SCR is done. Then we'll discuss about MOSFET, okay, BJT, MOSFET, and what more? IGBT. Okay, the characteristic and properties. Characteristics and properties. Okay, here one more thing we'll discuss, that is called rating of SCR. Okay, so when we cover this 6 part in this, and when we'll cover this 3 part, and some characteristic of switches, classification of switches, okay, then we'll also discuss about conduction loss, okay, average conduction loss, and switching loss. Okay, because numerical are asked from this area. Okay, and here also more part is there. Let me include here. This has 7, this is 6. Let us say this is 4, this is 3, 4, this, and this say 5. So here we'll discuss gate cathode characteristics of SCR. Okay, so this is all what we'll be covering. Here we'll be covering 3-phase half-wave rectifier again for different loads and for a different firing angle we have to check. Okay, so these are the parts that we'll be covering. Then the last one is inverter. Inverters. In inverters we'll be covering VSI, bridge, voltage source converter, and full bridge. Okay, single phase VSI, half bridge VSI, full bridge VSI. Okay, and then we'll compare their harmonic analysis and all. Then we'll have 3-phase VSI. In that I'll be covering 180-degree conduction mode, and 120-degree conduction mode, and the different waveform related to it, that is the phase voltage waveform, line voltage waveform and all. Okay, and then we'll discuss single phase CSI only, current source inverter, and then we'll go to this internal voltage control, that is called what? PWM, pulse width modulation. In the pulse width modulation also we'll have single pulse width modulation. Okay, we'll have multiple pulse width modulation, and we'll also have sinusoidal pulse width modulation. So these are the parts that I'll be covering. Okay. Okay, power semiconductor device will be having characteristic of switches, classification of switches, average conduction loss, switching losses. Okay, then from the SCR part we'll be having VI characteristic of SCR, about latching and holding current, on-state method of SCR, gate cathode characteristic of SCR, protection of SCR. There are different protection methods that we'll discuss. Okay, now from where numerical can be asked? See, numericals. Numerical will be asked from, see, from here MCQ can be asked, like they'll tell you identify the type of switch, which type of switch is there. Okay, so numerical belongs to this area. Okay, the numerical belongs to this area. Okay, Numerical belongs to this area. Okay, numerical belong to this area. Okay, then numerical belong to this area only, latching. Okay, numerical belong to this area, gate cathode characteristic. Okay, it has not been asked, but if it can be asked. Okay, numericals. Then here also numerical can be asked. Here also, mostly from this single PWM, numerical is asked. Okay, and this part, most of the numerical are asked. Okay, in the chopper part, I have left one more thing, that are called what? Commutation circuits. They are called commutation circuits. So in the chopper part, one more thing is there, that is called, because chopper and inverters are having DC supply, right? They are having DC supply, so they require a commutation circuit that can commutate the switch, that can turn off the switch successfully. Okay, so that the device is available for the next operation. So here I'll be having in the chopper part only. So this was say 3.1, this is say 3.2, and the 3.3 part will be commutation circuits. In which I'll be covering class A commutation, that is also called load commutation. Okay, class B commutation. See, commutation is nothing but the process of turning of the SCR. Okay, we'll discuss in brief. Class B commutation, that is also called resonant pulse commutation or current commutation. Okay, we'll have class C commutation, which is also called complementary commutation. Then we'll have class D commutation, which is also called impulse commutation or voltage commutation. Okay, we'll see the waveform as well for all these. Okay, so these are the parts that I'll be covering. Now the numerical that the gate have asked mostly is from class D. Okay, and there are some numericals that are all based on class B also. They have not asked many, but they have asked few, and here they have not asked, but still it can be asked. Okay, so we'll discuss one or two numerical from the here also, but we'll solve many numerical from class D and class B. Okay, so this was 4.1, 4.2, okay, and this is 4.3 CSI, this is 4.4. Okay, so these are the things, these are the contents that I'll be covering for what? GATE 2020. So write down. So that will be starting with our first topic, power semiconductor device. But before discussing power semiconductor device, I'll give you introduction to power electronics. Introduction to power electronics. Why we are switching to power electronics? We were already having signal electronics, right? We're already dealing with the analog and digital electronics, but why this power electronics came into picture? We'll discuss some of the introduction like advantages, applications of power electronics, objective of power electronics, disadvantages of power electronics, closed loop system that can be implemented in power electronics. Okay, all these we'll discuss. Okay. So complete this part. Okay, now let us start introduction to power electronics. So you got the basic idea of what all we'll be covering in our course of power electronics. Okay. Okay. Now see, first of all, what is power electronics? Okay, what is power electronics? First of all, it is a branch of electronics that deals with high power switches to meet high power requirement. Okay, now as the industry is emerging, with the emerging industry, they are requiring high power application devices. Okay, they need a high power application. So from where you will get? By using high power switches. Now from high power switches, that we can have different circuits from this high power switches, and the sequence of switches will give you the resulting current or the resulting voltage at the load, and that is how you will meet the load requirement. Okay. It deals with control and and conditioning of power. Okay, not only you have to control the things, you have to condition the power, like you have to create the conditions for, to meet the high power demand. Okay, then you have to see that your power requirement is fulfilled at low cost. Okay, your power requirement must be fulfilled at low cost. Okay, then the size and all will be the size of the switches and all should be compact. Okay, also there should be, or I can say directly that the power quality of the input and output must be good. Okay, so the power quality of the waveform should be proper, such that it results to less distortion. Okay, and you can have lesser harmonics. Okay, such that THD in case of AC will be less. Okay, total harmonic distortion. Okay, when you are using AC supply, you'll be having total harmonic distortion in the waveform, and when you are having total harmonic distortion will be used to see what content of harmonics or undesirable component are present in AC. Okay, and when you are dealing with DC, you'll be using ripple factor to see what content of harmonics is present in the DC supply, okay, or DC output. So all these will be using to analyze. So let us start with objective of power electronics. Okay, what are the objectives of power electronics? What are the objectives of power electronics? Development of power electronic converter with high rating switches. High rating switches. Development of power electronic converter with high rating switches. Development of power electronic converter with higher efficiency of conversion, because the converter has converter will have a converting tendency. Okay, it will convert AC to DC or DC to DC or DC to AC, so it must be converting that with a higher efficiency. Higher conversion. Development of power electronic converter at lower cost. Okay, when you are designing a power electronic converter, you must be techno-economic. You must be keeping in mind that the cost of that converter must be less. Then the converter should have, the power electronic converter should have, development of power electronic converter with less harmonics, that is THD, total harmonic distortion, should be less and RF, that is called ripple factor. Ripple factor should be less. Okay, this total harmonic converter we deals with AC. Okay, total harmonic distortion in AC should be less, and the ripple factor deals with DC. Okay, so DC ripple factor in DC should be less. Okay, because if they are having lesser THD and ripple factor, that means the waveform will be smoother. Okay, waveform smoother, and power quality best. Okay, so my objective is to design or develop a power electronic converter such that it should possess high rating. Okay, it should be closer to the characteristic of ideal switch. Okay, secondly, when you are designing a power electronic converter, okay, any converter will have a tendency to convert input to output. Okay, the input nature can be AC or DC. Similarly, the output can also be DC or AC. So it will be converting the input to output. So when you are converting that, the output must be close to the input. That is, output by input ratio should be okay, good, such that the efficiency should be high. Okay, then you must be able to design power electronic converter at lower cost, because if different companies are designing the power electronic converter, then that company will be given the priority which can do it at lower cost, because the user will be accepting at lesser price. Okay, then the power electronic converter that you are designing must be able to exhibit a proper and smoother waveform. Okay, much closer to true sine wave. If it is if the output is AC, it must be a pure sine wave or true sine wave. Or if it is giving an output as DC, it must be having a pure DC. Okay, having no fluctuations. Okay, no discontinuity. Okay, that waveform is considered as smoother, and for that waveform this THD and RF will be lesser, and the power quality would be best among in this kind of waveforms. Okay, so these are the objectives that I am aiming for. Okay, these are the objectives that I am aiming for. Now, so this was the objective. Now the thing is, sir, only converting is the main criteria here? No, because the conversion you can get with the machine part also. For example, if I talk about machine, okay, in machine also, if you want to convert AC to DC, you can convert by using different machine, okay, cascaded at different stages. Okay, for example, if I talk about machine part, okay, let us see in the electrical machines, if I want to have AC to DC conversion, okay, I can have, say, AC input, say electrical. Okay, then I'll be using induction motor which uses a three-phase AC input supply. Okay, the output of this will be mechanical. Okay, I'll be feeding this mechanical output to the prime mover of a DC generator. So this DC generator will be using mechanical output and it will be giving electrical input. But this electrical input will be now what? DC, sorry, this output will be now DC. So you are able to convert AC electrical output to DC electrical output. Okay, but the thing is, these two motors are what? Rotational. Okay, rotating in nature. So they will have rotational losses. They'll be having rotational losses. This rotational losses magnitude is more than the core losses or the copper losses, and that is why the efficiency of conversion will be poor. Okay, the efficiency of conversion will be poor. Okay, that is why I don't use machine for conversion. Rather, I would be using power electronics devices, such as for converting AC to DC. I'll be using rectifier, because it will have, okay, it will have good efficiency of conversion, and we can use high power switches in this, and this will have lesser losses, and moreover this will be compact in nature. Okay, this would not require a huge space. Okay, although these two machines require a huge space and huge maintenance as well, but power electronic devices will be compact and it would require less maintenance. Okay, less maintenance. And the last thing you have already seen, that the losses in the rectifier, that is a power electronic converter, will be lesser. So the losses will be less. Okay. So AC to DC rectifier, if you use, instead of converting it by the means of electrical machines, you will be having less size, less maintenance, and the losses will also be less, such that the efficiency of conversion will be more. Okay, here the efficiency of conversion was poor, and here the efficiency of conversion would be good. Efficiency of conversion is good. So that is why we don't use machine, rather we use power electronic converters. Okay. Now we can also implement, okay, a closed loop control system having a feedback. Okay, closed loop control system for power processing circuit. Power processing circuit. Say we have a power processing circuit. Power processing circuit is nothing but a circuit consists of switches at higher ratings. It consists of switches, consists of different combination of switches. Now this power processing circuit will be getting the input from power supply. Okay, power supply. Okay, it will be having low power circuit and a high power circuit isolated by a pulse transformer. Okay, so a power processing circuit will be there, and one more thing, a load will also be there. Load will also be there. Okay, which will have desired voltage, current or frequency. Okay, desired voltage, current or frequency. But what will happen that the power processing circuit will have certain sequence of switch. Okay, so in that sequence it may be possible that the V desired, V actual that you are getting at the output is not equal to V desired, or I actual is not equal to I desired. Okay, in that case you will see the load parameter, what the load is demanding. Okay, and in order to meet the desired load, what will you do is you will apply a feedback, okay, to the power processing circuit. Okay, this feedback will this feedback path, what will it will do, it will change the sequence in which the switches were operating earlier. So the new combination of switch will be giving you different voltage that may be equal to the desired, and once the voltage that you are getting from the power processing circuit is V desired, you will stop the operation. And this is how a closed loop control system will work here. Okay, that is what you will do, you will observe the load parameters, okay, voltage, current and frequency, and see if the actual load is equal to the desired load or not. If the actual load is less than the desired load, then also feedback needs to be incorporated, and if the actual load is greater than the desired load, then feedback needs to be incorporated, such that it will change the sequence or the state of the switch. Okay, this feedback path will change the state of the switch. Okay, that is which switch will be turned on, which switches will be turned off. Okay, so this feedback path will change the state of the switch, which will finally change the sequence of the switch. Okay, which will finally change the sequence of switches in which they are operating, or in the way, in the sequence that they are connecting it to the load. Okay, because switches will be what connecting the source and load. Okay, switches are only the means for connecting the source to the load. So if feedback path, if a proper feedback path is provided, it will turn the state of the switch in such a way that the sequence of the switches will be connecting the source and load in such a way such that you will be getting V desired, and the closed loop control system operation will be stopped. This is how a closed loop control system is incorporated in Powertronic circuit. Okay. Okay, now let us talk about applications of Powertronics. Okay, we'll see some of the applications. Although the Powertronic devices applications are huge, okay, from agriculture to aviation, and from low power fan, low power domestic fans to high power devices, okay, industry and all, these are used. Okay, from railway to renewable energy resource, they are used. Okay, so let us talk about some of the application of Powertronic devices. So the first application that we'll see is, okay, application of Powertronics. Okay, now if you see applications of Powertronics, first you see as like what are the applications of Powertronic in machines. Okay, so in machines you have speed control, right? Okay, because even in the machines, okay, if you're not able to control the voltage, control the current, control the speed, okay, then they are of no use. Okay, so we need to control, we must be able to control to get different speed. Okay, so because the different speed will correspond to different voltage. So speed control is needed. For example, in case of DC motor speed control, okay, DC motor speed control, what we do is we vary the terminal voltage, okay, and once the terminal voltage is varied, this EB, which is V minus IARA, will be varied. Okay, since this is varied, EB will be varied. And since EB is varied, I know that N is directly proportional to EB by phi in case of DC motor. So, since the EB is changing, the N will also change. Now, this voltage control is possible only by using some power electronic device. Now, which device will give you different DC voltage? So, I can use chopper, which gives the different output voltage. I can use a chopper to get, okay, so power electronic device I am using or not? To change the input voltage, input DC voltage, such that the EMF, the back EMF will change, which will change the speed, and this way you'll be able to do the speed control. So that is how the power electronic switches will come into play. Okay, now if we see a speed control of, say, induction motor. Okay, so this was, say, DC motor. Let me talk about induction motor. Induction motor speed control. In induction motor speed control, what I'll be doing is, I'll be varying the frequency. Once I vary the frequency, the synchronous speed, which is related as 120F by P, will also be changing. And in this way, the rotor speed, which is nothing but synchronous speed into 1 minus S, will also change. So this is how the speed control you are getting. But the frequency can be changed some power electronic device, and the power electronic device to change the frequency is cycloconverter. Okay, to step up the frequency or to step down the frequency, I'll be using, okay, cycloconverter, which is a power electronic. In that way, NS and NR will change and you'll get the speed control. Okay, let me talk about power systems. So in power systems, you use FACTS, okay, flexible AC transmission system, flexible AC transmission system. Okay, so in the flexible AC transmission system, we use some of power electronic converter, okay, and even in the bus, okay, we use static VAR compensator, static VAR reactor, okay, static VAR capacitor, VAR compensator, okay, thyristor controlled reactor, thyristor controlled capacitor. Okay, so all these devices will be using for compensation. Okay, because if I have a different bus, okay, that are connected by some buses, okay, say these buses are connected. Okay, now each bus will be having a different voltage. Okay, each bus will be having different voltage level. Now you must have studied load flow analysis, that if I want to change the voltage, okay, I need to have to control the voltage or to change the voltage at different buses, okay, such that load flow can be done. Okay, so if you want to change the voltage, you need to do reactive power control. So see, again control term is coming, reactive power control. And if you want to say change the angle between the load angle, okay, the load angle, you need to change or you need to have active power control. In this way, different buses will be controlled. If you can control the active and reactive power, then only you will be able to control the buses. Okay, so this is about the application of power electronics. If you see the third application, it is also used. See, in the control system, I told you the closed loop control system is needed, right? And it is also used in, say, renewable energy resources. Renewable energy resource. Okay. So change the voltage by changing the voltage at different buses. And how you can change the voltage? By using chopper. Okay. If you can change the voltage or rectifier. Okay, if you can change the voltage, you can have reactive power control. If you can change the load angle by some means, you can have active power control. Okay, renewable energy resources will have, like, say, solar cell. What does solar cell do? The output of the solar cell is DC, which needs to be converted to AC, because actual utilization of industrial and domestic requirement will be in the form of AC. So for again converting the output of the solar cell to AC, you need a inverter. Okay, you need a inverter. That is how it plays a role in application of power electronics. Okay, then we'll have transportation. Okay, transportation, like you must have seen railway cars, okay, in which single phase induction motor is used, okay, or traction, okay, like in DC series motor is used. Okay, again DC series motor will you need to control the voltage in DC series motor. Okay, so transportation, renewable energy resources, low power devices, okay, and high power devices, all the places power electronics play a major role. So this is about the application of power electronics. We'll take a short break. After the break, we'll discuss about advantages of power electronics, disadvantages of power electronics, about some harmonics, okay, and how disadvantageous is harmonic, and how harmonic can be danger, okay, to the input or output. Okay, let's take a short break of 5 minutes.